inertia around the edge of the rod, which I think would be something like 2 over 3 or 4 over 3, because it's sort of rotating 2L. So you can do that and you get the right answer. But for the second rod, you have to use the center of mass. Absolutely have to. I'm very glad you brought it up because it's a very, very important point that I must emphasize. When the whole rod is moving and no piece on it is stationary, you have only one choice. You must use the center of mass. The only way. Right. So we have now written down this. This guy. And we can now write down our total kinetic energy. Our total kinetic energy just is the sum of these two things. So we'll keep 1 over 6 ml squared outside. And what happens if we do that? Well, we have to do a lot of multiplication. Let's see what's in front of theta dot squared. Well, there's an 8 from here, but there's also a 4 times 3 times 3 from here in order to get this over 6. Yeah.
Can you please explain why we should calculate that at the same time?
Okay. There is a result which looks like kinetic energy to the half mass of the object times the velocity of the center of mass of the object squared plus a half inertia of the object at the center of mass over meter squared. Now, that result applies only when you do things at the center of mass. When we derive the results, I don't know if we're in class or if I've written notes, but the result when we derive it illustrates that it only works when things are calculated at the center of mass. It does not work at any other time. You cannot do this with an arbitrary point. What you can do is if some point on the object is fixed, I mean fixed, not moving, like the top rod, where that point is not moving, then you can write another equation. Kinetic energy of the top rod is equal to a half times the inertia worked around the point of rotation, the tip, times by omega squared. That's fine. But in answer to the earlier question, omega is the same in both cases. It's just the point that's fixed. I mean, the actual rotation of the rod is the same. It's moving at the same rate around the center and around the edge. It's just that the edge is fixed for this rod. I can compute the kinetic energy of this rod without working out the center of mass. I can just work out that. But for this bottom rod, I can't do that. Because what point on the bottom rod is fixed? No point. They're all moving. There's no fixed point on that rod. And because there's no fixed point on that rod, I cannot write this. I must write this. And when I write this, it can only be done at the center of mass. Right, that is absolutely essential. When the whole object is moving, you have to switch to the center of mass. You have to compute the inertia at the center of mass. Right. So let's get back to this one. What is in front of theta dot squared here? There's a 1 over 6, we've got an 8 from here, we've got a 4 times by 9 from here, 1 times by 9 because I want it to be over 6. So I times by another 3. Annoying arithmetic. 4 9 is 36 plus 8 is 44. Right, what's in front of phi dot squared? Something like a half turned into a sixth, which means it's just 3, or am I getting some other piece that I'm missing? Like this one. 9 and 3 is 12. Please correct me if I'm making mistakes, otherwise it's pointless. And finally, we have another 36 of these guys. I can actually check my answer at that point because in the type book, we were asked to only get to a certain thing. Yeah. I'll tell you in a second. No, it's supposed to be 44. It's in the book. So I'm sure that my correctness. The 44 comes from 8 plus 9 times 4. Remember, I need to get this over 6, so I multiply everything by 3. 3 times 3 is 9, times 4 is 36, plus 8 is 14. Alright, so we have our kinetic energy now finally computed, and our potential energy finally computed. Step 3 is over. What about step 4? We now need to find T tilde and U tilde. What do we do in order to find those? They're very easy to find. The first thing we work out is all the partial derivatives of U. I want to work out the partial derivatives of U. Del U by del theta is simply 8 mgl sine theta. And del U by del phi is simply 3 mgl sine phi. Working out the second derivatives, I get del squared U del theta squared is equal to 8 mgl cos theta, and del squared U del phi squared is equal to 3 mgl cos phi. By the way, what are the mixed partial derivatives? What are del squared U del theta del phi? 0. Right, this is only the theta and this is only the phi, so the mixed ones are 0. And therefore I can immediately write down my Hessian matrix. It's already computed. U tilde or U squiggle is equal to this one and this one, the diagonals, right? And the other two are zeros. So it looks like 8. Oh, and I work it out at the equilibrium positions. So I work it out at 0, 0. At 0, 0. What is this? What is theta? What cos theta with theta 0? 1. So this is just 8 mgl. And what is cos phi? When phi is 0 again? 1, 3 mgl. So this just looks like 8, 0, 0, 3 mgl. There's my U tilde. And T tilde is computed similarly. Again, we computed at the equilibrium position, so again we must substitute in 0, 3, and phi. But otherwise we must differentiate with respect to theta dot and phi dot. So for T tilde, I can get this down. So we're going to work out del T by del theta dot, and we're going to get is equal to 1 over 3, 44 over 3. ML squared theta dot plus a cross term plus 36 phi dot cos theta minus phi. Del T by del phi dot is going to equal to 2 12 of 24, 24 over 6 is 3, 4, 4. 4. That's a cross term. And cross term is 12. Shouldn't that 36 be divided by 6? Again, divided by 6 times theta dot x. Right. So we can get the Hessian matrix now by differentiating these again. And we get del squared t by del theta dot squared is simply 44 over 3 m L squared. Del squared t by del phi dot squared is simply 4 m L squared. Del squared t by del theta dot del phi dot is simply, differentiate this one with respect to phi dot, 6 cos theta minus phi. And of course, if you like, we could have put that, we could have done this one with respect to theta, we get the same answer. So the Hessian matrix, and of course, again, we're missing value at the set 0, 0 at the equilibrium point. And cos of 0 is 1. There's no more squares here that I've got. Right. So this looks like 6 all squared. So in other words, the Hessian matrix T total looks like 44 over 3, 6, 4. Right, yo. We've got T tilde and U tilde. The next step is to build this matrix and take the term to 0. We've unfortunately reached the end of our time for today. I'd like you to try this at home, try and get answers. And go and collect your problem books and check to see if you do indeed get the answer. There are all written down here for you to check yourself again. So it's good practice. Wednesday. I do have a Mathematica thing I do want to show you about doing this stuff in Mathematica. But I think we'll meet in the classroom and I think we'll finish this on Wednesday. So try and do it at home and then if you cannot, we will come on Wednesday. Well, okay, the first is going to come in one